we have several topics to cover: an overview of the testbed design and our current progress, and how standalone and non-standalone mode are supported. It is a service-based architecture which enables the distribution flexibility. Control and the user planes are separable, and the general hardware requirement is relatively low. We will cover more details later in the presentation. The run simulation and emulator are currently working, but due to its close connection with the hardware and we still have some stability issues, the remote support of the run part is currently not available. Other items more close to the applications are being developed and we'll keep you updated. Here is the license type for the open source software and platform that we are using. The license is, most of the licenses are regular non-commercial GNU general public license, except for the standalone part in free 5G core, it supports free commercial use as well. I think most of you are very familiar with this 5G standalone architecture. In our core network, it is strictly following this service-based architecture, supporting network function virtualization and other functions and mobile edge computing. Each network function is clearly defined and the configuration of the function is supported. For non-standalone mode, service-based architecture is also adopted. The non-standalone is R3. It supports R3 run compatibility, and MME, SGC, SGW, and the PGW functions in the 4G EPC are migrated to a 5G core, so which means that it's also a service-based architecture. For PCRF and HSS, it remains unchanged. Currently, it is difficult to find 5G standalone run in the market for testing. So that the standalone mode, service-based standalone mode provides a feasible approach to connect it to a non-standalone run. Although we currently have limited access to the radio hardware in the lab, we also include this page here for a near future reference. Our open programmable run is a USRP-based off-the-shelf run and physical layer instruments, including a Mari callbox, signal analyzer, signal generator, and wave judge. Please let us know that you need more information regarding any type of the hardware. How to clone the core system and distribute it in the locations that is needed is critical to support research in CCI. We adopted two ways of core network remote deployment, the virtual machine approach and the Docker approach. The operating system required to run the core network is Ubuntu 18.4 and the kernel is 5.0.0 on top of it. So we can use either way to deploy to desired location. The former one requires less pre-configuration from the users, and the Docker approach requires users to pre-install a specific operating system and also the kernel versions. So users can either conduct a core research on top of this or interact it with their own run system and applications. This shows the current plug-and-play deployment we have. You can let us know the IP address of your system that we can access, and so we will deploy the core network with the default settings there. And if you need specific configuration of settings, we'll work with you on the multiple runs for further support. Other options that will be supported in the future include access and contribute to the core, to the source code repositories, and access server for fetching the executable files, and also a sandbox solution. We'll open these operations in the future based on the need. Now let's get into the detailed features of our current 5G core network. Both the non-standalone and the standalone N1, N2, and N3 interfaces are supported. As a service-based architecture, each network function can be separated and virtualized, especially for user and control plane. So it is highly customizable for virtual use cases and dedicated networks. When combining with the mobile edge, with the multiple access edge computing, local offloading and backhaul control will greatly reduce the latency. It has a basic end-to-end support for non-3GPP hardware as well. Advanced features and demonstration for non-3GPP devices is still being developed, as well as the network slicing functions. So based on the features, we listed several use cases and research topics. The use cases serves as a bridge that connecting the platform implementation and the research capability. We also would like to hear more from you, from your opinion and comments on the use cases, how we can connect it better. For UE and the application-centric research, one use case in our testbed is to serve as a RAN and core network emulation to evaluate and demonstrate new concepts and use cases. For RAN-centric application, besides the emulation of UE and core network, our platform can also be used for hands-on implementations and enabling faster prototype. For core network, this can be used as a platform to evaluate and demonstrate new ideas in ciphering applications, in ciphering application function compatibility, operation automations. Adam will give a detailed introduction on these use cases.
So the evolution from 4G to 5G introduces support of control and user plane function separation. This decoupling enables the data forwarding component to be decentralized, allowing deployment and scaling so that packet processing and traffic aggregation can be distributed to the network edge. This decentralization also enables multiple deployment scenarios for data path diversity. In practice, this means the control plane can sit in a centralized location while the user plane is placed close to the application. CUPS-related research can minimize latency between core network functions, enabling 5G-specific low-latency use cases. Next slide, please. Can you go back one? Thanks. Network function modularity, as well as application and end device diversity, necessitates robust security features. Configuration of 5G network functions can enable security feature testing. This type of research can also uncover security vulnerabilities. Next slide. The session management function employs NAS signaling to interact with the data plane. The UPF selection function works in concert to enable mobile edge computing by selecting a UPF close to the edge of the network. Configuration and testing of this network function can improve performance metrics as well as network behavior under loading conditions. Traffic steering and quality of service can also be optimized. Service policy implementations can be studied and optimized as well. Next slide. The network exposure function enables connectivity between the 5G core and external applications. Smooth connectivity is supported by secure, scalable, simplified, and SLA-compliant service capability exposure for events, data, and functionality. RESTful APIs are used at the network interfaces. Configuration and testing of application compatibility can increase application performance, uncover security vulnerabilities, and enhance network performance as applications scale and diversify. Next slide. The modularity and scalability that network slicing introduces to 5G is massive. With network slicing, we enable a variety of new use cases with broad and disparate resource and performance requirements. Interactions of network slices dedicated use cases such as IoT, smart farming, military communications can be researched. Quality of service metrics can be determined and tested for the variety of use cases presented. Research into orchestration and deployment can enable creation of 5G networks of any size and purpose. Next slide. With the increase of services supported by 5G, configuration leads to increased operational complexity. Research into operations automation can enable parallel function of services with competing resource requirements. This provides opportunity to enable vertical applications in the core and can potentially decrease operational expenses. Back to you, Yang.
So another challenging area to implement is the interfacing with non-3GPP device. It is very different with interfacing with 3GPP devices, and especially in the case of IoTs. Research and the new concepts that enable offloading traffic to a Wi-Fi provider provides a great opportunity to reduce the 5G operation costs, and also it increase the capacity. In our current testbed, the GR Eternal enabled the non-3GPP functions. These are currently support in the standalone mode. However, it is very hard to find in the market for standalone mode supported UE. So we are exploring the operations on providing a general gateway for the current available non-3GPP devices in the market, and we'll keep you informed on that. So in the another area that we're also working on is on the V2X, and the demonstration function is still being developed. We'll also keep you informed on that. With the last use cases, this ends our presentation part of today's meeting.